Welcome everybody to week 6, day 1. We're going to be doing a little bit of computational geometry this week. Computational geometry is the graceful art of working with points and lines and things like that. So for example, let's say that you have some cities. You've got San Francisco, you got Fresno, you got LA, you got Bakersfield. Nobody cares about Bakersfield. All right, LA, you got San Diego, Vegas or something. And so a question that you might ask is, given these things, each one has an X and a Y location, right? If I were to click here, what city am I closest to? Geographical search, right? This is a thing. If you go to Google Maps, you search for coffee houses near me, it needs to return coffee houses near me and not in New Jersey or something, right? So, yeah, childishness is a state of mind, right? So how do I tell this? I could just do like a Pythagorean to like every city, or even worse, like if we're doing coffee shops near me, I could do a little Pythagoras, right? So we got like some sort of like Canada. There you go. Canada has got like Tim Hortons, right? They got a lot of Tim Hortons, and we could just like Pythagoras each one of those, right? And just search through all N coffee shops in the world and see which one's closest, right? That seems like an awfully inefficient algorithm, right? Hypot from you to every coffee shop ever. Exactly. There's got to be a better way, right? So this is one of those cases where order N is too slow, right? Especially to do it in real time. If you could do an offline thing where you can like pre-compute this kind of stuff, it's great. But what we really want is like some sort of like order 1 or order login. So order 1 means basically in a single operation you can find the nearest coffee shop. Login means if there's a billion coffee shops in the world, you can do it in a couple dozen operations, which is still not bad. All right. Store it into a tree one time and then look up. Store what? The location. How do you like if you have a binary search tree, you could store like X, right? This could be like the latitude or whatever, This thing is like flipping out. When I put my tablet over the wireless phone charger, it like starts flipping out. So you could have like X is less than 50 and X is this is 50 and X is greater than 50. But we got Y also. We got a problem here. It's not just sorting it left to right. That'll help somewhat, maybe, because then you could just, check people like kind of near you horizontally or something. But we're holding it horizontally and vertically, right? Yeah, welcome, boss. It's how are the tacos? So what we can do is we can do something called a Voronoi. Voronoi. I don't know. Were there tacos on campus? Very cool. Calculation. Okay. And so let's start with a simple one before we come back to this. So let's say we've got San Diego here, and we got Tijuana down here. Okay. Which points are closer to Tijuana and which points are closer to San Diego? If San Diego's at 0 across 10 up, and Tijuana is at 0 across, let's just make it 0, 0 to make the math easy. At 0, 0, it's at the origin of the world. How can I describe mathematically all points that are closer to Tijuana than to San Diego? Oh, you're at Graphs Lab? Nice. So which points are closer to San Diego and which points are closer to Tijuana? Obviously, if a point is down here, 0, -10, it's closer to Tijuana. Even if it's at like -20, -20, it's extra negative. -20, -5, that's closer to Tijuana, right? Everything below 0 is going to be closer to Tijuana than to ST. So mathematically speaking, Bruce, which points are closer to Tijuana and which points are closer to San Diego? Isn't there some circle representation? I mean, you could draw a circle or something and draw a circle, and now what? Form a straight line from ST to TJ, okay. What's the halfway point? 0, 5, all right. Yep, now what about a point over here? What if we're at like negative 26? Is this closer to San Diego or is it closer to Tijuana? Y2 plus Y1 divided by 2 is exactly right. So that's a halfway point, right? And we can average the X and the Y together. And then if we take the normal is a perpendicular vector. We can actually draw this out like this. It's perfectly horizontal because the two guys are vertically oriented. And everybody on the south side over here is part of Team TJ. These are all TJ coffee shops. And then up here, if we search for anything up here, it's going to give us coffee shops at this location instead. So let's say there's one Starbucks in San Diego and there's one Starbucks in TJ. If I search, hey, give me coffee shops near me, this will point you to the San Diego one. This will point you to the Tijuana one. Do you guys understand? So this is something called a Voronoi diagram. And this comes up a lot in video games, computational graphics. If you're trying to do computational geometry, sorry, if you're going to do graphics, they come up a lot. So what if we add a third city? Let's see if we can make this a little more complicated. But do you guys understand the basic thing here? Like, if you have 2 points, then a line sort of bisecting the universe between them divides it into Team San Diego and Team Tijuana, right? What happens if we add a third point? Let's add a point here, let's say. Okay. Well, let's get rid of these coordinates. I think you guys understand that now. We can do the same thing, right? We can draw a line between them and bisect it, and then draw a line this way. Try to do this as straight as possible. And this is going to be, I don't know, it's Hawaii, I guess. Hi. Okay. Okay. And so if I'm over here, then I'm going to get a coffee shop in Kahului. And I know it's not, neither is San Diego or Tijuana, but we're just saying this is the one Starbucks in all of Hawaii. So if I click here, the nearest Starbucks to me would be the one in Kahului over here. If I click here, the nearest Starbucks is the one in San Diego. Okay. And then we could do the same thing from Hawaii to TJ. Bisect. And have a line going kind of this way. That. And the kind of interesting thing is we don't need the bisecting line anymore. We don't need the bisecting line. We don't need the bisecting. Just erase this. So now we've got 3 regions. We've got the region over here, we've got the region over here, and the region over here. Okay. I'll erase it. It's gonna wipe out my. Maybe I can leave that. There. And if I erase this one, not too bad. Didn't lose too much. Okay. So, does this make sense? We've got 3 regions now. We've got the San Diego region, we've got the Tijuana region, we have the Hawaii region, right? So this is okay, fine. This is in Oahu. Okay, fine. Oahu, sure. The one Starbucks in all of Oahu. Okay. You guys see how this works? So you can sort of do it geometrically, right? You can draw a line, bisect it, and then you run the line to like the nearest like, you know, like we did this bisection, right? And then drew this line here, and once we hit another line, we stopped, right? Because that's further away from us. And same thing here. We drew this line and we stopped once we hit this line here. We started on the halfway point here. This one goes up infinitely. This one goes down until it hits a line, and then we stop. And oops, that's too much erasure there. And there we go. So you can just keep doing this ad infinitum. We can add Cabo down here. So we draw a line here, bisect, draw it out here, draw it out here. This one goes infinity. This one stops here. See how this works? So we've got a new region. And so if I search for coffee shops near me here, it's going to say Cabo. I'm on a ship, obviously, in the middle of the Pacific. I cross over some imaginary line, give me the nearest Starbucks to me, and it'll say, oh, it's in Oahu. Please swim north for 2,000 miles. And there's a lot of chat going on right now, but I hope you guys understand this method. Okay. So, so it creates these kind of like almost like skin cells, right? If I create another one here, they're convex holes, right? We talked about convex holes last time, so I don't know. This would be Oaxaca. Yeah, like skin cells under a microscope. You're not a. This isn't your hobby, staring at skin cells. Right? Kind of, right? See what I'm saying? No? They're not exactly round. Like, these are actually like polygons, right? They're actually Voronoi. Like, you can actually use Voronoi diagrams to generate, close-up scales and skin cells and things like that, right? So I was saying in graphics, this thing actually comes up a lot. Where was I? Oh, Oaxaca. Oh, Lord. Did I actually spell that right? Holy smokes. Okay. All right. Oaxaca. All right. So we draw these bisection planes. Nope, didn't get a straight line here. You buy yourself a pair of Air Force Ones. Amazing. And so this one will go out to here. Now this guy is the nearest one. So we need this first bisect. Come down to here and stop. Up to here and stop. Okay. Erase that. Erase that. We need this. Okay. I think we're good. And we'll extend down this way. These are infinite lines, right? So every time you add a new point, you get a new cell. And then once you have this Voronoi representation, it's very fast. Just click, here's the nearest coffee shop. Click, here's the nearest coffee shop. Or what's the weather, right? So if you have the weather, and there's different weather stations, then, maybe you do some interpolation or whatever, but, you could just find the weather near me, and it'll give you the weather. Like we have a lot of weather stations, it'll just give you the weather nearest you, right? Yeah, it's a Nelly Air Force Ones, right? I go stomping in my Air Force Ones. Now, how can we do this? How can we do this if we're doing like a grid-based system? So let's say that we're just going to do something like, oh, I don't know. the homework you're going to do. Voronoi, misspelled, of course. Run it. And so for this homework assignment, you're going to scatter what are called seeds. These things here are called seeds, seed points. And then you, what? Yeah, this is your homework. So you randomly pick locations for, it's like you scatter bird seed on the ground, and then you generate a Voronoi diagram out of it. So you see here we've got, I don't know, Nebraska and Kansas, and there's a line running right between them. And this spot here, is closer to, if I could select it, is closer to Kansas. And these spots over here, which again, I can't select individual spots for some reason, is near to Nebraska. Yep. Once we get over to here, these spots are all closer to Berkeley. I don't know. Okay. And so basically, you're just going to colorize the map based on which city they're closest to. Okay. So I guess C is Carthage. Where is Carthage? Oh, it's this one way over here. Yeah, so you can see that Carthage is, in fact, the biggest city-state. And so we're essentially, like generating a map, right? Like for a video game. So, yeah, the Berkeley versus Nebraska border, it's hotly contested. This is due in a week. This will be due in a week. So, it's easy, dude. Like, I'm not lying to you about this either. Like, what you do is for every row, for every column on the screen, you can just do a Pythagorean to it, to every city, and see which one's closest. Right? So for this point here, you can just Pythagorean distance. What's my row? What's my column? What's the city's row? What's the city's column? Use our good friend Pythagoras and just see, okay, the nearest city is F. And so, you're going to output in whatever the color of city F is. And each city just gets a random color. And every time you do this, you're generating a random map. Now with, if you're going to be doing like AAA game development, they're going to do things like add rivers and like mountain ranges. And they're going to round these things off so that they look nicer. There's something called a relaxation that you can do on it, which kind of makes them like you'll sometimes get things like this one here, the Massachusetts where Harvard is. You can see we've got this really like skinny toothpick looking country here, and so those are kind of like two. Yeah. So if you want to do a relaxation, you can see that you've got these toothpick-looking things here. And every time you do that, they kind of round off a little bit more. But if you do it too much, you end up just getting very regular, very even, very boring-looking countries that look like this. So, generally speaking, Frankfurt's the biggest country. Congratulations, Frankfurt. So generally speaking, like one relaxation kind of rounds it off a little bit. Gets rid of the worst of the things. We'll talk about that next time. You don't have to worry about it. You skip this assignment, so you don't already have it. Okay. So it is actually easy. Like I'm not like gaslighting you guys on this. For every row, for every column, do a Pythagoras to every city. And whichever one's closest, you print its color to the screen. That's it. Okay. So it's a triply nested for loop. No. That sounds slow and literally not the algorithm you just taught. I know. Because I'm trying to make it easy on you guys. Now, if you guys want, we can revise this to do the geometric, thing here. But I'm suggesting you guys just brute force it. Because here's the thing, like, despite the fact that this is a for every point on the Earth, do a Pythagoras to every Starbucks on Earth algorithm, and so you have to choose which level of scale you're going to operate at, every square kilometer, every square meter, whatever. You can just run this once, right? And you can run it offline. So you just have a data center just running, and it runs overnight, for every square kilometer on Earth, writing down where the nearest coffee shop is, and you just save it. And then later on, when somebody comes in and clicks and says, "Hey, what's the nearest coffee shop here?" You're like, "Oaxaca," and you're done. You just look it up. It's an easy lookup, right? Because you just save whatever color it is, to your data structure, and you're like, "Oh, our nearest city is Madrid." There you go. So, there's a starting code base. Yeah, I don't think you guys need starting code, but I think there is. CD Voronoi, misspelled again. Yeah, there's a whole README file on this. Yeah, it's easy. All right, them main.cc. So, So for every square on the screen, there is a tile associated with it, which holds the index of the owner. So, for example, city 17 owns me, and then if there's a letter to print there, because we print the letter of the name of the city, we hold the letter if it is going to print a letter. Every city is given a random color. The name of the cities by default is Fresno 1, Fresno 2, Fresno 3, Fresno 4. You can make a random name generator if you want. Okay. So, do you guys know what a static variable is? We need inline here. Oh, it's a yeah, maybe we do. Never mind. Okay. So a static variable, when associated with a class, is a variable that is attached to the class and not to each instance of the class. So in other words, every object of type city shares the same variable called .cat. So if I have a city down here, and I make a city called Paris, like that, and I make a city called Berlin, like that. If I say Paris dot count equals 12, and I see out Berlin dot count, this will print 12 to the screen, because Paris and Berlin are part of the same country. Yeah, so don't worry too much about what the keywords mean. Here it just means the variable is inline. You can have a whole lecture on that. Inline was originally used as an optimization keyword, meaning this function should be inline, which means you remove the function call entirely and just put the body of the function into it. It's like if you have inline int foo return 42. And down here, we can say, like, paris.count equals foo. What inline would mean is, rather than doing a function call and jumping up to the code to run foo, and then taking the value 42 and putting it into the return register and returning back, and then moving it out of the return register, it would actually just do that. That's what the inline keyword sort of originally meant. But it's sort of advisory, and optimizers nowadays probably ignore it. It probably doesn't do anything as far as optimization goes these days. You can try it and see if it makes a difference. I can't speak for, no, it's not an old habit. See, here's the thing. So the way that these things work, if you have a reserved keyword in a language, that means nobody can use it, right? And so if you're going to be adding functionality to a language, if you were to make a new reserved keyword, you would probably break people's code, right? So nobody has a function called inline. You can't do this. This is a reserved keyword, right? You can't have a function named inline. You can't have a function named friend, right? You cannot have friends in C++ as a function. Friends only exist inside of classes. Yeah. You can't with a capital F, that's true. That is true. Okay. And that's one of the reasons why, we do capitalization the way we do it. So, so one of the things about language design is that if you have these reserved keywords, and these have been reserved for a long time, that nobody has a function or a class named friend. And so maybe if you're going to add a new capability to the language, like let's say you're going to add parallel processing into C++, better than it is right now, which is fairly marginal, you might be like, all right, well, the friend keyword isn't really being used here, so maybe we can modify the language so we say return friend 42. This isn't valid C++. Please don't think it's real. But like they do things like this. So like, okay, well, that's a reserved keyword. It can't be used like this at all right now, period. So we know this is valid. We're not going to break anyone's old code. And so they do this all the time. Like with the auto keyword used to mean something completely different, but it was a reserved keyword. And so they knew nobody could have a variable named auto because it was reserved. And so they repurposed it. And so now you can have inline auto foo, right? And that's valid C++ now. Didn't used to be. Auto used to mean the variable was allocated on the stack. Nobody cared about because everything was allocated on the stack anyway. If you didn't specify auto, it was allocated on the stack. If you used auto, it was allocated on the stack. So it was a reserved keyword that did basically nothing. And so, but it was reserved, and so they repurposed it, right? So, I have two friends. Yes. So, what if you wanted to add functionality, then you use one of the existing keywords? So, what does inline do? So, inline these days, the myth is it's used for optimization. It might be. Probably not, though. Optimizers are much smarter than you. So, and me. So, and me. Like they're pretty smart. Like optimizers are pretty good, and they know pretty well how to make fast code. So they're probably going to ignore that. They might not. You can experiment with it. Reality. This function can violate the ODR. Is basically what it's used for. So the ODR is the one definition rule. Now, if you do this, it's still not going to like it. So what do you mean it can violate the ODR? If you end up including, like if you put this into a header file and you include it from multiple different means, like if you include colors.h here and you include it again a second time via other means, like you include something and include something, then you're going to have this function in two different source code files. And then if you link them together, you can violate the ODR. Let's put it this way, in the linker. Be a little more precise. Because it's not violating the ODR here. The ODR is the one definition rule, right? So the ODR means you can't redefine things like this, right? Like you can't have two functions with the same name and the same parameter list, right? You can't, if you have integer x as a global, you can't have another integer x as a global. This violates the one definition rule, right? You can only define something once. But what if you have inside of one file a global named x, and inside of another file you have a global named x? Now you violated the ODR. When you try linking them together, it doesn't know which one you want. Okay, and so the header guards protect you from including it twice. But what if you include it into a.cc and b.cc, then you link them together? Which version of the source code do you use? This isn't... Okay. Let me... Okay. Sure. Well, we're done with Voronoi. You guys got Voronoi. All right. Let's talk about C++. All right, so remove main.cc, then main.cc. Let me explain this. Once I had a student think that every time you make a function, it's got to be called foo. Yeah, see, it's warning you it's going to lead to an ODR violation. So I'm not using that acronym like lightly. Like this is something. Okay, so vim main.cc, and we can let's just return foo. Okay, so we got a program here. Don't care about you. All right, so we've got no CN or COUTs or anything like that. We're just keeping this old school. You see how fast that compiled? It returns 42. All right, so we included this function here. Let's see here, vim and vim main.cc a.h. So we got a couple different tabs here. So we got a header file that has a function. We got u that calls a function. Everything's hunky-dory, right? Everything's fine. There are only two valid function names, foo and var, exactly. Okay, so if I were to include this file twice, I'd have a problem, right? We have now redefined foo, right? Because remember, when you hashtag include something, it copies and pastes the file. And so if we were to g++ -e main.cc, you can see that means show me what main looks like after I pre-process it. You can see that here we have included foo twice, right? We've included a.h from line 1. We've included a.h again. Here's line 1 here. And we've got essentially this line of code and foo twice inside of main.cc. We have violated the ODR. It doesn't compile. You guys with me so far? Like, do you see why this is causing a problem? Because we've got foo twice now in our code. So how do we resolve this? You guys know the answer to this. How do you stop a header file from being included twice? Not inline. Pragma once. Or header guards, one or the other. So that's one way you can do it. Another way you can do it is if and def bill is cool, hashtag define bill is cool, hashtag and def. So either one of these will work. I personally prefer pragma once because then I don't have to come up with a new name every time, which usually is just the name of the file. But if you copy and paste the file, you can screw that up, and it really screws up your thing if your header guards get broken. So I like pragma once. I let the compiler figure it out. Can the compiler be fooled? Yes. Can it cause problems? Yes. But it causes less problems in my experience than using header guards. Okay, so if I compile main.cc now, we're going back to working again. So even though we include it twice, with a header guard, we stop it from being included twice. That's not the problem that Inline fixes. Let me show you the problem that Inline fixes. So let's say that I've got another file called b.h. And b.h is going to have a function called bar, because those are the only function names allowed. And bar is just going to return foo. Okay. So main is going to include A and B. B is going to include A. Okay. Everything works fine. Now, what if this was instead a.cc file? I'm going to move b.h to b.cc. Yep. Then main.cc. Turn bar. And instead of you, we just say int bar like this. g++-c b.cc, g++-c main.cc, nm b.o. So the object file contains two functions in it. It's got bar and it's got foo. Main.o has two functions, or three functions in it, main and foo, and it's got a call to bar. U means I'm calling this function, but it doesn't exist here. So if I come into here, see, I've told C++ this function exists somewhere, but not here. That's why when I look at the .o file, I got a U there. The U means it's undefined, it's elsewhere. And the T means it's in the text segment of our code here. So here's the problem. Now we have violated linker version of the ODR. Okay, so this object file has a copy of foo. This object file has a copy of foo. If we try linking them together, b.o, main.o, then we get a violation, multiple definition violation. You guys see that? That's what inline fixes. So inline allows you to fix violation, the multiple definition violation, at the linker level. Okay. So the devil wears pragma. Nice. Does this make sense to you guys? Inim is a program that tells you which functions are defined inside of a .o file. And we've got a full definition of foo inside of B, and we've got a full definition of foo inside of main. And when we put them together, we don't know which one to use. Just think about this. Watch. If I edit a.h and have this one return 43, now these are different versions, right? So if I nm main.o, this version here is returning 43. This version here is returning 42. We've got two different functions with the same name, same parameter type that are different. Which one do we use? I don't know. Yep. Do you guys see the problem here, or are you just memeing on chat? Which is fine. Like I like it when students are engaged. So here's the solution. Done. Notice how the warning went away. The warning was there because if you have a function in a header file, you're going to get those violation warnings. Okay, if you include them for multiple .cc files. So you put inline in, which again, originally, like, and what even today most people think inline is an optimization thing. It's really not. This is what it solves. Okay, so if we were to recompile everything, g++ -c b.cc, nm b.o, look, g++ -c main.cc, nm main.o, look, if I run it, g++ main.o, b.o, it's no longer found within the .o file, right? So instead, in fact, it's actually probably getting optimized away. But if it was a bigger function, let's maybe make this not get completely optimized away. One of the best ways of stopping the optimizer is to do random stuff. So sran 0 return rand modulus 42. Time doesn't exist. What is time? C time. Okay, so g++ -c b.cc, g++ -c main.cc, g++ main.o b.o. Normally you'd have a makefile, handling all this for you. Main.o, and you can see it's still getting erased, but whatever. So like how you wrote a perm to kill the optimizer instead of just trying. Well, I don't even think the optimizer is on. Maybe. Yeah. So anyway, the point is that inline is a directive to the linker. Okay, and so all those symbols we saw there, T is in the text section, U it's undefined, and weak is what you will get when you actually have a inline thing that's not being removed. So I know I just fix everything I touch. I'm cursed. But the point is that a.h is that anytime you have a header file, if you have a function in a header file, you need to mark it as inline. Boom. There you go. Okay. So if you look at my read library here, yep, there, you can see all my functions are marked as inline, so that if you include, if multiple .cc files all include my read library, then they don't create link conflicts with each other. This is just standard practice anytime you have a header file. Now you might be asking about classes. Everything defined inside of a class is automatically marked inline. Okay. So it fixes the linker duplicate reference problem. It doesn't change, like I said, it doesn't change something like this, or like if you it doesn't fix something like this where you've got two functions with the same name. It fixes the link problem, right? It fixes the fact that you've got two copies of foo in two different .o files. When you have it marked as inline, it will just pick one of them and not give you an error on it. So, you don't understand? So if you have a .o file, right, these are the compiled versions of your functions. And a function can only be defined in one place, in b.o. So this guy it calls rand, it calls srand, it calls time, but it only actually has the source code for bar. That's what the T there means. So every .o file has functions in it. Well, I mean, I guess technically it could be empty, but yeah, every .o file has functions that it has written, and then it has other functions that it calls. And when you do the link step is this, b.o, railroad, main.o. This is the link step. This is not a compiler anymore. It's just taking all the .o files and it says, okay, well, main.o is calling bar, right? And so if I just try compiling the program with like main.o, I'm going to get an undefined reference, right? You've got a function that you're calling, and I can't find it. And so when I compile it though with g++ main.o b.o, then it finds bar, and then bar is going to be calling these guys. And so where are those? Well, those are in the standard library, which get linked in by default. So you don't have to worry about it. But like in old school C++, you would actually have to link in the math library, the math lab, libm is what it's called, the math library, in order to, otherwise, like if you call sine or cosine, and you don't link in the math library, you get an undefined reference to sine or cosine and things like that. Nowadays, the math library gets linked in by default. Well, yeah, we've already covered Voronoi, so I think you guys are fine on that. So as far as classes go, if we go back to the Voronoi thing here, inline here means something completely different. Because remember, inside of a class, everything inside of a class is automatically marked inline. So everything inside of between this bracket and this bracket, everything is marked inline. So that's why a lot of people just put classes inside of header files, because everything in a header file in a class is inline, and you don't have to remember to mark it as inline. So if you just have your functions inside of a class, inside of the header file, then everything's fine. You don't have to worry about that. So, nah, you guys are great. You guys are one of my most well-qualified IS50B classes ever. So this inline here, static inline here, is completely different. And so that means what I had earlier, where I had city Paris, city Berlin, Paris dot count equals 16, cout Berlin dot count, and this will print out 16 to the screen. Okay. When you have a static inline variable in a class, every object of that class type shares that variable. And so what we're using it for here is just to keep track of how many Fresnos there have been. The first time you make a city, it's going to be Fresno 1. We pre-increment it, so it goes from 0 to 1. The next time we make a city, remember every variable shares the same, every object shares the same member variable. It's now Fresno 2, then it's Fresno 3, then it's Fresno 4. So every time you make a city, you can track how many cities there have been, and then change the name to match it. And this is actually very useful for doing like instrumentation and things like that, where like if you want to know how many times a function's been called, you can make a static variable and just increment the count every time somebody calls that function. You do a little bit of quick and dirty profiling as a result of that. So, qualified, what's that? Yeah, and so static variables in a function are also completely different. These keywords keep getting reused because there's not a whole lot of reserved keywords. And so if I have static int Bob equals 0 here, this will get initialized once, ever. Every time you call print world, we can say Bob plus plus. Every time we call print world, it's going to increment Bob by 1. So when you have a static variable like this inside of a function, this is like having a global like this. Okay. Static means put a global it's a global variable that you can only see within this function. So you don't have all the problems attendant with globals. Globals are really gnarly because anybody can read and write to them. You don't have any control over that, right? So if I had a global named Bob like this, any of the functions can read or write to it, you know? And we're just trying to use it to just count how many times print world is called. But somebody could just set it to 12 and you're like, oh dear, you know? And so if you have it like this instead, this is a global function, a global variable, sorry, that is only visible within this function. And that's nice. That's the proper way of doing globals if you need global state that doesn't reset every time the function gets called. So statics weren't able to be modified. No, you can have a static constant, and now it's, you know, can't be modified. But yeah, you can certainly modify a static, right? And then static on a function is completely different. So like all of these keywords like static and inline and extra and things like that control things like how they're linked. They control the scope and visibility of a variable or a function or a class. They you know, if you want to be like a C++ master, it'd just be like CPP reference static keyword, and then just like have fun with that. There you go. So different uses, internal linkage, and so there's like different keywords to handle how they're linked and the lifetime of objects and things like that. So their duration. So, yeah, but that's kind of the important stuff there. While true, increment Bob. Yeah, you can do that if you want. Okay, so that's it for today. The Voronoi kingdoms. You make different seeds. You're going to scatter them across the world. And then you're going to run the Voronoi. This is the heart of it here. Where basically you just find the nearest city, and then you set the owner of that tile to be that city. And then when you call print world, yeah, let's get rid of this. We don't need these anymore. Print world, you're going to loop over every square on the screen. You're going to move the cursor there. You're going to set the color to the color of the owning city, and then print a space. And then that will color the screen based on the Voronoi diagrams. It's really pretty, and there's a lot you can do, like I said, with Voronoi. You can use them to make, you know, see. All right. Train generation and things like that. It's here's a Voronoi, yeah, for America essentially, right? So I think these are probably the capitals. No, maybe not. I don't know what's going on here. Is this EU4 maybe? Might be EU4. And so it shows you the nearest point to every center point of every province in EU4. These things they come up all over the place. It's just one of those things you probably want to know. All right, so that is it. Is there extra credit for your? Yeah, sure. If you guys want to do it. So the actual, by the way, if you're doing this, the way that they actually run it is they will sweep the world. It's called the sweep line algorithm. So they sort all the points from left to right, and they go in this way. And so you start off with a wahoo, right? And then you add this one, you draw the splitting line, you add this one, and basically you only need to keep track of like the last, I think, couple lines here. And so every time you add another point to the right, you just add, like before we added Oaxaca, it looked like this, right? And then we added Oaxaca, and then it all you have to do is check, I think, the nearest people to the left, and then add, do the bisect and perpendicular and add it. So you have to keep track of which lines are currently visible over here. Like these guys aren't, but these guys are. And then you just keep a running tally of like what's visible. And then you just keep adding. You add a new guy here, and come in here and do this and do that. So then you come up here and do that, and yep. So if you want, do the sweep line algorithm, I will definitely give you extra credit for doing that. I'm giving you the Seaside 40 version of it. Although, okay, so this is related to triangularization. We got the 58 people waiting for us, but Voronoi is actually related to what's called the Delaunay triangularization, which is a better triangularization method than what we used, where if you have a set of points, it creates triangles out of them. This is actually the same thing as the Voronoi diagram. It's just the sort of inverse of it. So given the seed points, so you can see the Delaunay triangularization is like sort of the complement of a Voronoi diagram. So it's kind of neat. It's the exact same thing, actually. So just drawn a little bit differently. Okay. So that is it. Read about that till your eyes melt, and then give up and do it the simple way with HiPot. Yes. Or not. I'll give you the extra credit if you can figure it out. All right. Thank you, 50B people. And if you have any questions about it, please post onto the Help Center. I hope you enjoyed our diversion into advanced C++ topics, as always. And you should be able to do it. It's not bad. All right. See you guys. Peace.